We have learned stochastic process in the fourth unit in time domain, and now we are going to learn the stochastic process in frequency domain. So the frequency domain parameters are, we call them as spectral characteristics. So before going to start this, let us see some prerequisites. First one, time domain signal is converted into frequency domain using Fourier transform. Many are there, but we are going to use Fourier transform. For example, there is a signal xt. On applying Fourier transform on this, it converts into frequency domain x omega. Okay, so x omega can be written as the Fourier transform of xt. Fourier transform of xt. So I'm going to write the Fourier transform formula. X omega is equals to integral from minus infinity to plus infinity xt e power minus j omega t dt. If you clearly observe on the right side, t is there, omega is there. On the left side only omega is there. On the left side we want only omega. On the right side two parameters are there, t and omega, time and omega. So if we integrate with respect to t, the left side becomes left side depends only on omega. And if you clearly observe on the right side, here is t and here is t, here is t. In place of t we can write u also, or k also. Here what you have to understand that t is there. In place of t some other parameters also there, but the structure does not change. Okay, so this is the Fourier transform formula. And inverse Fourier transform is there. Inverse Fourier transform means I would like to find out what is xt. I would like to find out what is xt from x omega. Then you need to apply inverse Fourier transform on x omega. So inverse Fourier transform converts a frequency domain to time domain. Fourier transform converts time domain to frequency domain. So xt is equals to integration from minus infinity to plus infinity x omega. This time we are going to write e power j omega t. Left side is t, left side depending on t, right side two parameters are there. So we have to eliminate omega, so we have to integrate with respect to omega. Okay, these are the Fourier transform and inverse Fourier transform formulas. And not only that, let us see some parameters in time domain. So time domain and frequency domain. So energy, I want to know what is the energy in time domain and in frequency domain. Energy can be obtained by integrating square of a signal. Integrations of square of a signal is always an energy in time domain. Okay, In the frequency domain, we have to integrate square of the signal. Here, what is the signal in frequency domain? X omega is the signal. Mod x omega square from minus infinity to plus infinity d omega 1 by 2 pi. Okay. In the frequency domain, I wrote mod x omega. After converting the time domain into frequency domain, the frequency domain consists of complex values. Complex values ante entiది x plus or minus jy. Okay. So complex, I want to know what is the energy. Energy is a magnitude. Energy is a value, not it's a real value. Energy is a real value, not complex value. So what you have to do? You have to apply mod on complex value. That's why I applied mod x omega. And the power. What is the relationship between energy and power? Can someone tell me? What is the relationship between energy and power?
Energy is equal to power square by 2.
Power equal to energy by time. So you have to divide the energy with time. Okay. So here the power is you have to divide this the power. I'm going to divide with 2t. Why I'm dividing with 2t means I'm integrating from energy is integrated from minus t to plus t. What is the duration? 2t. Okay. And not only this, it's hanging. Please wait. One by 2t integration from minus t to t x square t dt. Integration of x square t dt is energy by 2t. By 2t is a time. And you have to apply t tends to infinity for aperiodic signals. And here also 1 by 2 pi integration from minus infinity to plus infinity mod x omega square d omega. This is energy in frequency domain. You have to divide this with time. Okay. And limit t tends to infinity. These are the energy and power formulas in time domain and frequency domain. These formulas you will see in the next semester in the subject signals and systems. Okay. Now let us come back to our subject. In the fourth unit, we have seen the spectral. We have seen a stochastic process in time domain. There we have seen autocorrelation function and cross correlation function. These are the parameters in the time domain. Not only that, one more is there, convolution. Convolution also comes under time domain parameter and frequency domain. In the frequency domain, auto power spectral density PSD, cross power spectral density. These are the parameters. How to convert time domain into frequency domain? We have to apply Fourier transform. Okay. So time domain is the fourth unit and frequency domain is the fifth unit. Okay. So the first topic is power spectral density PSD. It talks about the power per unit bandwidth. Simply I am writing power per unit bandwidth. Can someone tell me what is the unit for this? Units ఏంటి? Power means watts for bandwidth, hertz for watts for hertz. Or these are I'm giving this shortcut definitions. Okay, power per unit bandwidth or distribution of power. Distribution of power over a range of frequencies. Over a range of frequencies. The power spectral density can be represented with capital S of omega. So I'm drawing the plot. X-axis is omega, y-axis is S omega, and how the power is distributed. How the power is distributed over range of frequencies. Let me say omega 1, omega 2. In this range, how the power is distributed? Is it varying or it is constant? Okay. So this is the power. This is the power in between omega 1 and omega 2. Okay. So what is the power spectral density? Distribution of power over a range of frequencies or power per unit bandwidth. Now let us classify the power spectral density. Power spectral density are two types. Auto power spectral density. Second one, cross power spectral density. I said that by applying Fourier transform, time domain signal is converted into frequency domain. Okay. Now I want to know what is the auto power spectral density. So what is the input? What is the time domain signal? Autocorrelation is the time domain signal. You have to apply Fourier transform on autocorrelation. That gives us auto power spectral density. Similarly, you have to apply Fourier transform on cross correlation. That gives cross power spectral density. Now, this auto power spectral density is represented with capital S. Double X means auto. S omega is power spectral density. Here also S omega, but it is cross power spectral density. So SXY. Okay. Auto power spectral density, cross power spectral density. Now let us begin with auto power spectral density. S double X omega. Okay. So this S double X omega can be obtained by applying Fourier transform on R double X tau. Okay. So what is the Fourier transform formula? Integral from minus infinity to plus infinity. So where we are applying the Fourier transform? We are applying the Fourier transform on R double X tau e power minus j omega tau d tau. Original formula t untadi. Here we are using tau. X place lo autocorrelation function on S double X omega. Okay. And other formula S double X omega is equals to limit t tends to infinity expectation of mod x omega square by 2t. This is a also power spectral density. And I want to know average power. I want to know what is average power. So P average, that is 1 by 2 pi integral from minus infinity to plus infinity S double X omega d omega. Area under a power spectral density gives you average power. Okay. So these are autocorrelation and auto power spectral density relation and auto power spectral density formula. Okay. Now let us see the relationship between auto prospector density and cross correlation function. Relationship between auto prospector density and auto correlation function. This is also called as Wiener-Khinchin relation. Relationship. What is the relationship? R-X tau, apply Fourier transform on this, it gives auto prospector density. This is the relationship between auto prospector density and autocorrelation. In the statements, auto prospector density and autocorrelation function form a Fourier transform pair. This is the relationship. So R-X tau and S-X omega, these two are a Fourier transform pair. This one we have to prove. Let us consider a signal, a random process. Xt is a WSS RP. Okay, it exists between minus t to plus t. Between minus t to plus t. Okay. Now we have to find S-X omega, and we have to prove that it is a Fourier transform of autocorrelation function. Just now we have written the formula, limit t tends to infinity, expectation of mod x omega whole square by 2t. Okay, what is x omega? X omega is a Fourier transform of xt. So x omega is equals to integration from minus infinity to plus infinity xt e power minus j omega t dt. Okay. Now let us say this is equation 1. In the equation 1, what we have to find? Mod x omega square. This is unknown. After finding this, let us apply expectation of mod x omega square. Can we write mod x omega square as x star omega and x omega? Can we write? What is x star into x or x star? Is it not mod x square? Complex numbers. X star is a conjugate. X star is a conjugate. Okay. So let's take x omega as integration from minus infinity to plus infinity. X not minus infinity plus infinity. Let us take minus t to t. X t1 e power minus j omega t1 dt1. What is x star omega? You have to apply conjugate on it. So conjugate is applied on x complex numbers. Conjugation is applied on complex numbers. So in x omega, xt1 is xt is there, e power j minus j omega t is there. E power minus j omega is a complex number. Am I right? It is cos theta minus j sin theta. So cos theta minus j sin theta is a complex number. For that you have to apply conjugate. So how can we write it? Minus t2t. Let us write xt2. I am writing just as xt2 and e power j omega t2 d t2. So let us apply mod x omega whole square is equals to integration from minus t to t x t2 e power j omega t2 dt2 into integration from minus t to plus t x t1 e power minus j omega t1 dt1. Now let us find out what is so before that let us write integration from minus t to t, integration from minus t to t x t1 x t2 e power minus j omega t1. Let us take minus j omega common. Minus j omega common. Then it leaves us t1 minus t2 dt1 dt2. This is mod x omega square. Now let us find out expectation of mod x omega square. So you have to apply expectation on this total formula minus integration from minus t2 plus t, integration from minus t2 plus t xt1 xt2 e power minus j omega t1 minus t2 dt1 dt2. We know that expectation is applied on random variables. So where are the random variables? xt1 and xt2 are the random variables. So let us apply expectation on those two. So you have to apply expectation of xt1 xt2 and e power minus j omega t1 minus t2 dt1 dt2. And if we clearly observe, this is the autocorrelation formula r double x t1 minus t2 tau. Here this is tau, where tau equals to t1 minus t2. The difference between it is a time delay. Tau is the time delay t1 minus t2. So let us rewrite it. Integration from minus t2 plus t minus t2 plus t. It is r double x tau r double x tau and excuse me. Let us write it as a t let us go in other way. Let's take T1 equal to T and T2 equals to T1 plus tau or T plus tau. So dt1 is equals to dt and dt2 is equals to, I am differentiating with respect to delay. So dt2 equals to d tau. The second one, in the second case, I am differentiating with respect to tau. In that case, t is constant. Okay. So limits, you know that. So limits changes. So what are the limits? Minus t minus t. Other limits are minus t and t minus t, because t2 that one expectation of xt, t2 is t plus tau e power minus j omega it becomes tau dt d tau. This is expectation of mod x omega square. What is autocorrelation, auto perspective density formula? Limit t tends to infinity, expectation of mod x omega square by 2t. So let us apply expectation of mod x omega square is double x omega is equals to limit t tends to infinity 1 by 2t integration from minus t to t integration from minus t to t minus t expectation of xt plus tau e power minus j omega tau dt d tau. I am arranging in another way. Integral from minus infinity to plus infinity, limit t tends to infinity 1 by 2t integral from minus t to minus t minus t. Here the limits are not important. You can take minus infinity to plus infinity dt. I am taking this as inner integral. Outer integral is e power minus j omega tau d tau. Now if you clearly observe, this is the time average of autocorrelation. Time average of autocorrelation function. Okay, so time average can be represented with a of what, or double x of t plus tau. Okay, already we said that xt is a wide sense stationary random process. For a wide sense stationary random process, this time average and ensemble average, and this is equals to autocorrelation function. So finally, s double x omega is equals to integration from minus t to plus t r double x tau e power minus j omega tau d tau. Okay, so this is the relationship between perspective density s double x omega, the Fourier transform of r double x omega. we need practice to derive this. I am repeating this one. We have to prove that the perspective density is the Fourier transform of autocorrelation function. So for that, I have used the equation 1 is Wx omega equals to limit t tends to infinity expectation of x mod x omega square by 2t. So first I have taken mod x omega square as x star omega x omega. So in x omega I have taken the variable t1. In x star omega I have taken the variable t2. Multiplied those two. So that gave us mod x omega square. So we want expectation of mod x omega square. So apply expectation on the random variables. So where are the random variables? xt1, xt2 are the random variables. Here I have used a variable separation method by taking t1 equal to t, t2 equal to t1 plus tau, and finally we obtained that expectation of mod x omega square equals to integration from minus infinity plus infinity. So you can take minus infinity plus infinity also, okay, or you can take minus t to t. Why I have taken minus t to t means I assumed that xt is a wide sense stationary random process in the interval minus t to t. మీరు minus infinity plus infinity తీసుకున్నా no problem. Okay, so you have to apply this expectation of mod x omega square in the perspective density formula and simplify this. So here we got one formula, time average formula. Okay, if we assumed that xt is a wide sense stationary random process, and that too it is a ergodic in correlation formula. Okay, if I have to say strictly, this is not only wide sense stationary random process, it is ergodic in correlation, autocorrelation. What is in ergodic? Ergodic means time averages and ensemble averages are equal. So ergodic in correlation means autocorrelation time average is equals to ensemble average of correlation. So xt is a random process along with ergodic in correlation. Then we have obtained that the perspective density is equals to Fourier transform of autocorrelation function. Okay, so we see the we will see the properties tomorrow. Let's go one by one slowly. CR.
Good afternoon, sir.
Yeah, good afternoon. Tell me the absentee numbers.
Yes, sir. Sir, 61, 65.
Wait. Yeah, 61, 65.
79.
Okay.